Welcome everyone for today's lecture. It's my pleasure to introduce Michael Genesereth. He is an associate professor here at Stanford in the computer science department. He has degrees in math and also physics from MIT and Harvard. Throughout his career, he did various things, including founding companies, but he told me that's not of his primary interest right now or anymore. He's really into academics with a strong focus on logic. And one of the items he researches is general gameplay. So what it is, he will of course explain much better than I can. But the main idea is, certain programs, computer programs that can play games very well. For example, Deep Blue, that is the best, or was at the time, the best chess master, certainly beating human players. And so the thing is, these kind of programs are very good at one particular game, but not in others. And what he's interested in is, like, how can we make software that we can put any sort of game in front of them, and the computer basically learns the rules along the way and plays it very well. And I also think there's a very nice and interesting connection to humans. I mean, the way children learn, right, is by playing throughout their childhood, also without not really knowing the rules. And so there's a deep connection here, and I leave it with that. So you're very welcome.
Well, as Ingmar suggested, I'm a computer scientist, and my interest is in making computers that can do interesting things, play games in particular. I'm also a teacher, and as such, I've been using computer technology to teach massive open online courses, so-called MOOCs. And one of the key things we do within our MOOCs is to use games for education. So the two themes you mentioned in the introduction are exactly my interests right now, making computers able to play games and also using games to make education much better. Today I'm going to be talking primarily about the former, though it turns out there are some connections to the latter that I can allude to at the end, or if you'd like, you can ask me about it if we have time after the discussion today. Okay, so general gameplay. Ingmar, you gave a brief account of that. Let me say that just a little more detail. So we're all, I hope, in this room familiar with games and why they're so interesting. Here I'm speaking of strategy games as opposed to physical games like soccer, baseball, and so forth. And strategy games are great because they allow us to exercise our intellectual abilities, test our intellectual skills, and the competition in the game is usually good because we can then pit ourselves against others and sort of see how well we're doing, and if need be, improve that, or at least evaluate how well our game-playing strategies are. So that's why we like to play games. In the early days of artificial intelligence, which is where I've done most of my professional work, it was thought that those same arguments could be used to justify and to evaluate what might be intelligent systems. So the idea being that if a system is more intelligent, it ought to be able to play games more effectively and win more games. Less intelligent, win fewer games. So maybe game playing would be a good subfield of artificial intelligence to use in testing the abilities of our increasingly intelligent computer programs. So game playing was from the very earliest days of the field of artificial intelligence, now going back over 50 years, has been an important subsegment of that field for this reason. But there are some limitations and critiques. Many people who look at game playing and artificial intelligence have critiqued it for a couple of reasons. One of those reasons is that game-playing programs tend to be good at one thing and not good at another. So Ingmar referred to Deep Blue, which has beaten the world chess champion, but it's not a very good checkers player. It can't balance a checkbook. It can't do anything but play chess. It does one thing, does it very well, but can't do anything else. And it can't adapt to do anything else. That's all it can ever do. So the question then is Deep Blue, can we consider Deep Blue to be a truly intelligent program? It surely is a good chess player, but is it truly intelligent if it doesn't have that kind of breadth of capability that human beings have? So it's not, and the other view is, if you look at Deep Blue, even within chess, how intelligent is that program? Did it figure out how to play chess, or was it told how to play chess? There's a strong argument that many people have made that the intelligence of these specialized game-playing programs primarily rests with the programmer of those game-playing programs rather than with the programs themselves. The programs basically are following a recipe. Imagine a recipe book. If you follow the recipe to make a nice dish, did you invent the dish or did you just execute the recipe? It's the person who invented the dish who might be viewed as being the culinary expert as opposed to the person who simply makes the dish. Similarly, a chess-playing program has been taught what to do in many situations or to evaluate under certain conditions what to do, and then it does that. But the real intelligence could be viewed as being in the programmer of the game-playing program rather than being in the program itself. So for these reasons, game playing has often been criticized as not a great test of intelligence. So does that mean it's out the window, we can't use it, it's not interesting? Well, no. And a few years ago, general game playing came along as a way of still utilizing the good parts of game playing, but at the same time fixing these fundamental problems that we saw with specialized game playing. So what exactly is general game playing? So general game players, as it says here, are agents. I'm going to use the word more generally, whether we're talking about humans or computers, are agents that are capable of playing strategy-like games, chess and the like, based solely on information that is supplied to the game player at runtime. So translation into normal English, the game players don't know the rules of the game until the game begins. So the result of that is they can't be programmed to play any specific game by the programmer because he has no idea what the game is going to be. And the result on the program itself is that, first of all, there's a certain amount of versatility. These general game players can play a wide variety of games, not just a specific game as Deep Blue can. And they can play games that they have never seen before, but also nobody has seen before. And typically in general game playing settings, we give games to programs that have no human being has ever seen except for us, much less the systems themselves. So versatility and novelty is one of the features one gets here that Deep Blue couldn't even begin to illustrate. Okay, so that's the basic idea. I hope that idea is clear. I'm going to spend an hour less with you talking about some of the interesting issues that come up here. But hopefully the idea has come across. Is there anybody who has a question about what it's about? Okay, then let me move ahead with this. Well, this idea, as I said, began about, well, actually, it's almost 10 years now. I guess I've been giving this talk for a few years. It's just 10 years now. It's its 10th birthday this year. And what we did in order to kind of make general game playing a popular thing to work on was we established a competition in connection with the Research Association for Artificial Intelligence called the AAAI, the Association for the Advancement of Artificial Intelligence. And every year there's an international competition that pits the best general game players against the other best general game players to see who really is the best. And that has been going on for 10 years right now. And here are some of the winners here. There's Jim Clune, who's getting congratulations to the very first winner of the very first competition. He's being congratulated by Ron Brockman, who is the president of the association, and a big smile on his face, pride at having won. Also, he got $10,000. So I'm not sure where the smile is coming from, but at any rate, he has multiple reasons to be smiling. And then we have Michael Thielschur and Stefan Schiffel, who won the second one, and Sam Schreiber, one of the winners one of the year, and Omar Finson, a winner, and the most recent winners, Andrew Rose and Stephen Draper. And over the years, we've had these various different pieces. Now, I put up the pictures of the people, but that's actually not what I should have put up, because what they did was to create the program, but actually it's the program that's now winning the games. It's the one who figures out how to play them. These guys don't. In fact, they are often beaten by their very own players on those games. So worth realizing that we really give the award to the player, not to the programmer. Anyway, so along with the general game playing competition, oh, there they are. As you see, it's actually been somewhat international. The USA has only won 3-4 times of the 10 or so times here. There's also, in addition to this general game playing competition that pits automatic players, computer players against each other, there's also a carbon silicon competition in recent years to pit the best humans, or the best computer programs against humans. I can't say it's the best humans because we don't have a human general game playing competition. And so we do is we take some bright people and have them play against the computers. And by the way, when we play this, what do you think the outcome is? How many people think the computer wins? How many people think the human wins? Interesting. So a mix. By the way, I saw you all. It was about 50-50, roughly 50-50. The answer is, the very first time that they played, the human won. We actually gave the human a situation where it had a forced win. It can force the win, and the human found it. Ever since then, the human has lost. So unfortunately, we human beings are not doing too well at general game playing in this, at least according to the rules that are set up here. This is Chris Welty, who is, by the way, one of the inventors of the Watson program that won the Jeopardy, beat the human players at Jeopardy. Unfortunately, he couldn't beat the general game player himself when he was pitted against it in the competition a couple of years ago. So we're not doing too well, and I'll explain a little bit, maybe a little later on, why it is I think we're not doing too well. And I will say that this is slightly prejudiced competition because the circumstances are that the human only gets a few 10, 15 minutes to look at the game and then has to play according to a clock of about 1 minute per play. And that's a little hard for humans. If the human were given several days to look at the game, the humans, I think, would generally come up with strategies that would be superior, and they might be able to win these games. And so far, if we were to give the rules of chess, or games that the user knows, the human knows, the human will beat the program. However, it's a game that the human has not seen, it's not quite so clear. Okay, well anyway, there's that. All right, so what I want to do now is spend some time, that's kind of the overview. I want to spend some time talking about what actually goes into general game playing, what are the issues here, and along the way I'll try to highlight some issues which I think are broader than computer science, though this original talk was sort of intended for a computer science audience. I'm going to try to make it more broadly appealing. If you have questions along the way, please ask. All right, so there are a number of elements that are necessary in order to make general game playing a practical reality, and I'm going to go through those three elements and then get to these more or less interesting issues about how you actually do general game playing. So the first is, how do we describe games? Remember, I said that in general game playing, the game description is given to the program at runtime. So what's the form? So you can imagine we break open the box of the game, take out the rules, and hand the rules to the program. That's not what we do. And the reason we don't do that is we have chosen not to make natural language processing a part of the competition, which would be necessary in order to do things that way, because usually those rules are written in a natural language like English. Instead, what we do is we have found another way of presenting those rules, which I'm going to talk about now under game description. Okay, well, first of all, let's talk about before I get into that and what the form that is, let's just remember what we mean. Just to give you an idea of what we mean by game. So general game playing, multiplicity of games, no restriction on the games, except that they're all sort of strategy games, mental games rather than physical games. And that would include things like Othello or Chinese checkers or diplomacy, or the ever-popular I Love Lucy version of tic-tac-toe or checkers. So some of these are two-player games, like this one. Some of them could be six-player games. Some of them have communication, like diplomacy, where the players can talk with each other. Some of them are more traditional. I guess tic-tac-toe and checkers are pretty straightforward. Okay, so there's a wide variety of games, as well as I've suggested, games nobody's ever seen before. But just to give you a sense of the kinds of games that we're looking at, these are the ones that you might think about. So abstractly, mathematically, from a computer science perspective, what all of those games have in common is that one can mathematize those games in a certain way. And the typical way we use is to think about the games as some kind of state machine. What do I mean by that? It means that at each point in time, the world of the game, the state is in some state, like S1. And then the players make their moves. And then when a player makes a move, that causes the game to go into another state. For example, a piece is moved to another square of the board. And so it goes to another state, and then another state, and another state. So there's one starting state, and the idea is that the game is over when the game reaches one of these terminal states. It's a slightly darker circle there to indicate the terminal state. And along the way, there are values that the agent gets for being in this particular state. Typically, we only care about the values at the terminal state. You know, we care whether we won or lost, but every state has a value for a variety of reasons. Okay, so that's a tip. Any one of those games I just showed you can be modeled in this way, like what the state of the tic-tac-toe board is, where the X's and O's are, where the pieces are in a chessboard, so forth. They can all be modeled abstractly as some kind of state machine. Is everybody comfortable with that idea? Okay. What about multiple player games? We got two people moving, so what happens then? Well, in fact, we would like to make sure that we can accommodate both alternating move games where one person plays, then the other person plays, but also simultaneous move where both people play at the same time. Diplomacy is like that. You have multiple players playing at the same time. So the way that's modeled is kind of a so-called multi-agent state machine, where at each state you get a pair of moves. Each of the players makes a move, and that leads to a new state. And a pair of moves leads to a new state, and so forth. But basically, it's still a graph. States are the nodes. Actions, or in this case, pairs of actions, or 6 tuples of actions, are the arcs which lead to other states. So for us, a game corresponds to a graph of this sort. That is what we mean by a game, with a starting state and some ending states and some values on the ending states to determine who won, or at least what the values were of those positions to the players. By the way, the games need to be zero-sum. Many of the games you look at, zero-sum means that if one person wins, one person loses. Some of the games can be cooperative. So if you end up in, well, this is a zero-sum because it's 0 for one, 100 for the other, 100 for one, and 0 for the other. But it could have been 80-80. So if you get to one state, they both get 80 points rather than one getting 0 and one getting 100. That's OK. OK, so we wanted to model cooperative games as well as strictly competitive games, and they all fit within this framework. OK, for right now, you should be thinking that a game is fundamentally a graph of this sort. OK? Now, so I've just given you a mathematical model of the game. How can we tell the game the rules of the game, which are kind of implicit in the way the states are connected? How do we tell that to the computer program? Well, you might think all we need to do is to take this graph and some kind of linearize it into a series of bits that we send to the computer program, and it's all done. Not so easy. Since, well, as it says here, since all the games are in fact strictly modeled in this way, one could in principle do just that. You could in principle just find a way of linearizing that graph and sending that sequence of bits to the player. Unfortunately, the state machines can be very large. If you take the game of chess, for example, the number of states in chess, the number of possible states, nobody's ever done the correct computation. I don't know who's done the correct computation, but somewhere north of 10 to the 30th states. So if you think about how long it would take to transmit the graph from the game manager to the game player, you would realize we would be here for centuries before it would ever get across. And besides, just nobody has enough memory to store that thing. There's no way we can actually take that graph, which conceptually makes sense, and ship it to the players. So we have to do something else. And what we need to do is find a compact description of the game rules rather than this extensive description of the game rules that is simple but big when represented as a game graph. And so what's been done is partly what made this whole field go was the invention of a so-called game description language, which is a formal language based on logic, which allows us to codify exploiting the regularities of that game graph, allows us to codify the rules in a compact form and to ship those rules to the players in a relatively small amount of space. So just to give you a sense of what that looks like, I don't expect you to read this. Intentionally, the font is small. But just to give you a sense of what rules look like, I put up this little sample. These are the rules for tic-tac-toe. Now, again, I don't want you to know it, but just to ground you a little bit in this, let me just briefly point out a couple things here. So these statements up here are the statements that say what the initial layout of the graph of the tic-tac-toe board is. So at the upper left-hand corner, cell 1-1, for row 1, column 1 has a B or a blank. So 1-2 has a blank, so all 9 cells are blank, and it's X's turn to play. So the start of the game is characterized. That's the state of the start of the game. Each player has some legal moves. One of the legal moves is to mark a square. You can mark a square, XY, if there's a blank in cell XY. Otherwise, you can't mark the square. And what the other player is doing at this time is doing nothing, passing, in effect, no op. no operation, do nothing. Because this is an alternating move game, unlike simultaneous move games. There are versions of tic-tac-toe where both players try to play at the same time, in which case there would not be no-opping, they'd both be trying to mark. All right, next says if you do something, if player P marks a square, then that square is going, sorry, the first one up there, that square is going to be marked afterward. So it's sort of are the rules that sort of simulate how the game moves from state to state. These next things tell us that. And this tells us that the game is over, it's terminal, if there's a line of marks of one player or the other player. And here are the values for each of the states. And then there's some helper things to find over there. Okay, but that's all of the rules. So there's 5,400 states in tic-tac-toe, possible states in tic-tac-toe, but they all fit onto one page. The rules fit onto one page. If you look at chess, with its 10 to the 30th plus states, the rules fit on about 4 pages. So you've got an enormous amount of compaction of the description, and that description can be sent to the players. Now the challenge, of course, is how is the player going to use this information to now play the game, and we're going to talk about that in a minute. But at least we've solved the problem of getting the rules sent to the player in a compact form, which actually captures everything about the state of the game. Okay, there's only one more. You don't need to know this, but just I think it's kind of quirky and interesting, which is that in order to avoid having programmers look for special words in the description that might mean something to them, and they are going to kind of get and build that into their program in some way. In fact, we changed the names of all the words in the description. So instead of writing cell, mark, and white, and so forth, those all turn into just nonsense words. So the player can possibly know in advance what these words mean. The only things that are meaningful are these keywords like does, next, true, in it, and so forth. So there's only 10 words that are known. They have to do with the way the language, way rules are described, rather than having anything to do with what the world looks like. So so-called obfuscation is part of the whole. Yes?
You use the word player to mean the computer.
We use the word player, whatever, the computer or the human. The human also gets the same thing. If we play human carbon silicon, right? Same for the very same reason.
You're good at reading these rules.
Well, you have to understand the language. Now, I have to say, in the human competitions, the humans are actually given a lot. First of all, they are given a picture of the state of the game, so they don't actually in the normal competitions they don't actually see this. In the early competitions, this is what they saw. But in a real general game, that's what they should be seeing. But we actually make it easy for the humans by showing them a picture of the state. We also make it easy for them by showing the legal moves in every state. So they don't even have to compute what the legal moves are. They still can't win. Yes, sir?
Okay, what's the purpose of the obfuscation?
Again, because people could build things in, and the idea was you don't want people building in the chess rules and say, this is a game of chess. I know how to do that. I'm going to get out my handy-dandy chess subroutine. We don't want them doing that by looking at the words. Right? If they can recognize that it's chess by the structure of the game, that's a different story. But they're not allowed to use the words.
So this is why I asked the question. When you say they, do you mean the general game playing program, which might have chess?
Correct.
Okay.
Correct.
Not a human.
Unless the human is a player. The player, whether it's the program or that. But the programmer is out of the picture. When general game playing starts, the programmer is gone. He can't touch the program, right? It has to be the player, whether it's a computer or if it's a human playing a computer, then it has to be the human. Okay? Both of you guys.
I got it.
So your human players will tell you, yes, I really understand the legal moves, and they're not constrained by their inability to read logic.
Again, in the early days, they should be doing this. I mean, to be fair, they should be given this. But we found that the humans have so much trouble that we've given them extra help to deal with this so they don't have to read logic rules. That's not fair in some sense to the computer, because we could also give the computer specialized data structures, right? And the computer could then use to play that game effectively. But we don't want to do that. We want to keep it absolutely neutral. And so properly, in a proper general gameplay setting, they should be seeing these rules after having training about what logic is, how to read logic rules. But that's not what we do today in order to help the human. The computer players always get this. Right? They never get anything else. Any other questions on that subject? Interesting questions. Okay. All right, so two more pieces. One more piece, and then we get to how to do general game playing. So the next piece, just to set the stage, is, okay, how does a general game playing done? How do you conduct a general game playing match? What happens? Okay, so typically, by the way, it says where game management is the process of administering a game. How that's done is there's a program called the game manager who actually runs a game, tells the player, helps the players run a game using something called the general game playing protocol, which I'm going to show you briefly just to show you that's very simplistic. It's not a big deal. The big deal is how you play the game. So typically there's a game manager, which is a program running on the web somewhere. And a game director comes and says, I want to have Bob play against Ingmar. Two programs play against each other, and here are their IP addresses, their internet addresses. And the game manager then communicates with Bob and Ingmar and says, okay, you guys are going to play a game. Here are the rules of the game. Go. Start playing. So the game manager is a program running on the web which is using the web to communicate with the players. There are three kinds of messages, just to show you what happens. There are three kinds of messages that typically take place. I've already said what happens first is the game manager says to Bob and to Ingmar, you're going to play a game. Here's the name of the game, or the number of the game, the identifier of the game. You're going to be playing white. Here's the game description. Here's that set of rules in that language I just showed you. So that's all you're ever going to hear about the game, is you're going to see this set of rules. You've got so many seconds before the game actually starts, and then you've got so many seconds to make each move. Typically, this is on the order of a few minutes. Typically, this is on the order of about a minute or so. Varies from game to game, match to match. Okay, so that sets it up. Now, once the start clock comes in, the players have the opportunity to think about the rules for a while. Again, sometimes on the order of maybe a few minutes to hours to think about the rules. But the human programmers are not permitted to look at it at this point. After the start clock expires, the manager sends a move. It says, okay, I need your move, play. All right? And we'll talk about what that is in a second. So play this thing, and now after play clock seconds, the players are expected to give their move, their first move, back to the manager. And then this repeats until the game is over, at which point the manager sends them a message that says, okay, game's over, stop. That's the whole thing. All right, that's what happens. You have start, play, stop. So pretty simplistic here. There's nothing interesting going on in the manager talking to players. I'll just mention one thing here. What the play message does is it contains the name of the match you're supposed to be playing, but it also sends the actions that you both made on the last move. Why is it doing that? Why does it have to send the actions? If it didn't send the actions, what would happen? You don't know what the other player did because you're not looking at a board, right? All you got is the internet. So in order to figure out what the other player did, you have to be told what the other player did. And you're told what you did for a reason, which I'll mention in just a second. So you're told what all the players did. Yes?
Is this what a human player would see in the carbon silicon competition? They would just see a list of the actions?
Again, it has progressed to the point where we show on the screen the actual state of the board, and we give them a drop-down list of legal actions. Right? So much more information is given to the humans in the carbon silicon. Okay, so there's that. Now, question is, what happens if a player does not move in time? Or what happens if Ingmar makes a crappy move? I mean, an illegal move. What happens then? So that's a good question. If you're going to run a competition, you have to decide what are the rules. What happens if somebody doesn't play and the clock expires? Well, there's two possibilities. One is he's lost. Game's over. The problem with that is that when you're playing computers against computers, sometimes computers don't respond for a variety of reasons, like they go down, they've lost their internet connection, and you don't want to have the other player win simply because some other player crashed or the internet went down or the internet connection went down. So we still want the other player to still win the game, and what happens is the manager in that case will make a random move for the player who didn't play in time. And so the other player still has to beat random moving in order to actually win the game. Now, if Ingmar makes a bad move and the manager substitutes a legal move for your bad move, that doesn't mean you're necessarily out of the competition, though. You could still win the game. But you have to know what move the manager made for you. In order to do that, that's why the the manager sends back your move, the move that it made for you, not necessarily the one you said to it, because what you said to it might have been wrong, might have been illegal. So it's the move that you actually made on the board, and it sends the moves of all the players. So there's a little bit of subtlety there, but that's all there is to it. Okay, done with the subtlety. Okay, so now we've got the players. They've got a description. They've got this manager who's asking them to make moves. How do they play games? All right, well, this is where it gets interesting. This is what it's all about. Okay, so first of all, I'm going to go through 3 levels of complexity here to kind of get to what the meat of general game playing is all about. So first of all, games can be, once you've got that game graph, you can build what is called a game tree by starting at the initial state, taking all the possible legal moves the moves that are legal in that initial state. Remember those legal sentences in the description. And then you use the next information in the description to figure out what the next state will be. Then for each of those next states, you figure out all the legal possible moves, figure out what the next states are going to be, and you keep doing that and building the game tree until you get to a point where every state at the bottom of the tree is a terminal state. The game is over. Okay, once you've done that, you've built this entire game tree, and now a player can just look at that tree and analyze it to determine, well, what would be my best move in this position? Well, that's going to be a certain amount. What would be my best move in this position, and so forth, all the way back to the beginning, in which case it decides what's my best move at the start, and then it makes that move. So this is called complete game tree search. You search the entire game tree to find the best move, right? We all know how to do that. And the problem with that is what?
I thought that's what you started with the chess on.
Sorry?
I thought that was the problem you started on in chess. It's intractably large.
No, the game graph is intractably large. The graph, what happens if you make this move, what happens if you make that move, what happens. But you're right, you're on the right track. The game tree now is also intractably large. Right, there's the game graph, which is the set of all possible games, and now there's you're looking at this from my point of view, what my moves would be. How big is this game tree? And it's exactly the same issue. It's too big. You can't store it. You can't search it in any reasonable amount of time. Anybody can we can easily do tic-tac-toe. That's, computers will do that in a fraction of a second. But when you get to more substantive games, they can't do this. Okay, so typically what happens in game playing, not just general game playing, this just says what you just said, is typically you get to a point in the tree where you've searched part of the tree, but you haven't finished. Now, how do you decide what to do? So I don't know. I haven't gotten to the end of the game, so I don't know which of these is going to get me to a winning state. But how do I choose now which of those two moves to make? So any suggestions?
Yeah, I wanted to ask, didn't you have a description also for one state you could see how well the score is doing, right?
I have for its current, but remember I only care about the value at the last state.
It only gives you when you're in it.
That's correct. So if the game were over at that point, that's how much you would get. But the game's not over there, so you have to wait until you get to the end to know whether it's... And there's no correlation between those two scores.
Unless there's a game that has part of the rules that has scoring.
And one of the interesting cases is one where the game is so-called monotonic, where actually the scores do reflect the scores in the intermediate states do reflect the values of the terminal states. But that's rarely the case. Like chess, you don't get anything unless you checkmate your opponent. What I didn't want you to say, and what nobody said, I'll come back to your thing in a minute, is, oh, well, you count pieces or board control. Those all make sense in chess, but they don't make sense in many other things. They are meaningless. You don't know what the rules are, so you don't know what those are. But what you just cited was some cool stuff, which was, in fact, the primary approach used to general game playing in the early days, 2005, 2006. Just exactly what you said. Let's look at how much freedom you have, how many moves you have, and so forth, as kind of a sense of how much power you have at this point in time. So that's maximize mobility, Barney Pell's introduction. Let's do exactly what Bob suggested. If you got more moves, that's a better state than one where you're hemmed in a corner and you can't go very far. That's a bad thing to do, but if you're out in the middle, that's good, because you have many things you can do. And maybe symmetrically, you want to minimize your opponent's mobility. You want to box your opponent into the corner, and so that he can't play as well. So those are cool ideas, and they in fact were used in the early days and produced a semblance of interesting play. There's also how close you are to the goal, but that's a little hard to evaluate in some cases. Some cases it's easy, other cases it's hard. But these two are pretty easy to evaluate, and there's nothing that doesn't talk about any particular game. They're good heuristics, techniques that may work and do work much of the time, but they don't work all the time. So,
address that for a minute? Are you defining mobility in terms of the number of possible moves against the possibility space of all moves that are there?
the number, so if you've got two states,
So it's freedom you're measuring, not mobility.
yes.
Yeah.
It's mobility. It's, if you look at this, sorry. Oops, that's not what I wanted. I wanted this. So you might compare this one to this one. Now these all have the same number of, the same mobility. So, okay, all right. All right, so that's what these guys wanted to do, but it doesn't always work. And here I wanted to give you is Jim Clune, who built Clune Player and won the first ever general game playing competition, came back to defend his title the second year playing against Flux Player. And this was a simplification of the position in a game of checkers. Now, I don't know how much you know about checkers, but basically you're moving on the odd squares. Every other square's got a piece. The black's trying to go up to the top, and the red's trying to come down to the bottom. And each player's trying to take all the opponent's pieces. And when you wipe out your opponent, you've won the game. So Clune Player here is playing red against Flux Player in black. And so you're allowed to move on diagonals. If you move in front of another player, that player gets to jump you and take your piece or pieces. If you have a jump, you're forced to take that jump. You must take the jump. If you don't have a jump, you've got to do whatever you like. Or if you have multiple jumps, you can pick one. But you must take a jump if there is one. And so here we are, black trying to move up, red trying to move down. What should red do at this point? It's trying to preserve its pieces and trying to get to the other end of the board while preserving its pieces, or alternatively try to take as many black pieces as possible. What should red do here? Now, it's a pretty weak position, but what should it do to try to keep the game going? It's not a hard question. Move the back piece. Right. Right. Sounds like a good thing to do. What do you think Clune Player did? It pushed this piece. I think it was it pushed this piece. Sorry, pushed this piece here. It jumped, it pushed that piece there, and lost the game. So what in the world was it doing? Well, it was doing what Bob suggested, which is it had looked at the game briefly during that start clock period and had figured out for whatever reason that limiting its opponent's mobility was a good thing. I'm going to box my opponent into the corner. This is a good thing to do. So now let's look at this game again. What are the rules of the game? How could you limit the mobility of the opposing player here best? You make him jump because he's forced to jump if you give him a jump. So this game was a beautiful example of Clune Player giving away piece after piece after piece after piece to black. And that's how it got into this terrible situation at the end. It just kept giving its pieces to black because it thought limiting mobility was a good thing. Not always, apparently. And so this was, very sad for poor Jim Clune. And it led to a new generation of general game playing programs, which were based on Monte Carlo search. And this is possibly the single biggest increase in performance so far has come because of Monte Carlo search. The basic idea is this. You start at a state of the tree. You begin to expand the tree. At some point or other, you cannot expand the tree anymore because you're running out of time. So you still have to evaluate these states. How do you evaluate them? Well, the idea of Monte Carlo search is rather than trying all the possible ways to play the game to the end, just make some random moves from here to the end of the game. I'm just to choose one move in each state until I get to a terminal state. It's very fast because you're not considering any choices. You're just choosing one thing. Did I win or lose? Won this one. Now do the same thing here, 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 and here. Now go back and do it again. And do it as many times as you can before you run out of time. When you've done that, you've looked at, say here, you've played the game out 4 times. And in this case, you've gotten an average of 25 points. And in this case, you've gotten an average of 50 points. Here you got 0, and there you got 75. Pick the one that has the highest probability of leading to a success. And in this case, this would be the move to make. So what happened was, after Monte Carlo came along, suddenly general game playing programs got really good. They started beating people routinely at this point, as well as playing very interesting games with each other. What do you think is wrong with Monte Carlo search? Why is it not the end of the story? It's playing randomly. It's not even considering what the other player is going to play. It's not thinking about strategy. It doesn't know anything. It doesn't even know there are pieces on the board. It's just sort of saying, this move, which one gets me to a win? It is no strategic thinking whatsoever. If there's one winning space, one winning state in the entire game graph, and if it happens not to find that, everything's going to be 0. It gives you no direction at all. So it's not really an effective way. It does produce very good behavior in many cases, but it too is not the winner. Well, we don't have a guaranteed solution to this, because if we did, we'd have solved a very fundamental, difficult problem. However, what we're looking at now, and now that we've moved beyond this period, is the new generation is so-called offline processing. And offline processing means during the start clock, the part before you even begin to play the game, you spend a lot of time thinking about how to optimize the gameplay, figure out regularities, see if there are any rules or heuristics that you can find, and then to automatically, and then to use those rules when you start playing. The trade-off is that sometimes looking at the game description, which is small, right? It's not 10 to the 30th states, it's small. Sometimes you can process the game description, amount of time which sort of grows polynomially with the size of the game description. But you can get benefits that have exponential benefits in terms of the gameplay. You can make the game play astronomically faster by doing a little bit of work by looking at the game description. I'm going to give you 2 examples of this. Actually, in the interest of time, I'm going to give you 1 example of this. Game of hex, which I'm not going to show you because it's a little complicated. This one. It's called Hodgepodge. It's a game of chess glued to Othello. So in the game of chess glued to Othello, what you do is the board consists of a chessboard glued to an Othello board. And a move consists of a move on both boards at the same time. And then your opponent makes a move on both boards at the same time. There is no such thing as, that's one move of the game. Okay, so how complex is this game? If you think about the branching factor of chess, how many possible moves do I have at every point? Let's say there are A possibilities. And if you take the branching factor of Othello, B, there are B possibilities. How many combination moves are there? A times B, right? For every A move, there's B moves at the other board. So A times B possibilities. So the tree has a branching factor of A times B. And so if you look at how expensive that is at n steps down, you'll find it's A times B to the n. That tree is growing exponentially in A times B. But is that the best way to think about searching this game? You don't have to do that because, in fact, whatever you move here is independent of what you do here. What happens on this board cannot affect what happens on that board. So you don't really need to do that. All you need to do is search down for A moves here and separately B moves here, but you don't have to cross multiply them, because if you try A1 here and B1 here, it's going to be the same as A1 and B2, the effect on this board. There's no cross-board coupling. So the idea is to factor this game into multiple independent factors, and by doing that, one decreases the cost to A to the n plus B to the n. It's still exponential, but it's a sum of exponentials rather than an exponential of a product, which is dramatically smaller, hugely smaller, and allows you to search way deeper into the tree before you have to give up. It may even get you to the end of the tree. So the question is, can you do game decomposition? Well, it turns out that there are techniques for doing this. As I said earlier, sometimes the cost varies. You can actually look at the game description and recognize by looking at the description that this is factorable into 2 games. And there are techniques now for doing that, which are similar to what we do when we see the games, when we would see this game. But the computer, of course, has to figure that out just by looking at those rules with the well-cool Hillman-Noig, or whatever those crazy words were. It has to figure out that these games are factorable, even though it doesn't actually say it explicitly in the description. Okay, so this is where a lot of the action is. Look at the description beforehand and spend time understanding the game, playing the game. By the way, there are other examples like Triathlon is a game where you have to win one game before you can start playing the second. And then you have to win that game before you start playing the third. You have to finish that game, before playing the second. Finish the second game before playing the third. So clearly, there's no need to search to the end of the tree, the overall game tree, in order to stop at this first inflection point before you do that. So you can actually sort of horizontally factor rather than vertically factor the games. So there are some techniques for doing this, and that's kind of emerging now. And it's interesting because those techniques are the techniques we use when we build programs of all sorts, not just game-playing programs. What's going on there is that the player, during the start clock, is programming itself to play the game. It's very much like what the programmer of the original game player, like Deep Blue, is doing when he's building Deep Blue, except that we've replaced the programmer with an automatic programmer, which is looking at the game rules and saying, I'm going to build a player to play this game. And then that player is going to play the game using Monte Carlo or whatever, but the point is that a lot of this other processing is going to take place in advance. And this is why we're interested in this from a computer science point of view. We want to build systems that can take descriptions of worlds, and what we want our computer systems to do, and can figure out an appropriate algorithm to use to operate in that world. So this is more than game playing going on in general game playing. It's actually a sort of study in computer science in general. And to do that, what we're doing is take the experts. I don't know if you folks, if you're not computer scientists, you don't recognize Don Knuth. Maybe if you're a computer scientist, you do. Who wrote kind of the first comprehensive book on algorithms. And what we're doing is we're taking his knowledge of algorithms in those books and trying to build it into our general game players. So we can use that algorithmic knowledge to build general game playing programs. And then there's also Jonathan Schaefer, by the way, who's kind of the premier game playing expert in the world at Alberta. So we want to combine those two people in our general game playing box. That's what we want them to do. We want to be as good as Knuth plus Schaefer at building programs to play games. All right, so I'm going to skip remarks in the interest of time. You can ask me later about relationship to game theory and so forth, if you like. Just to conclude. It's just a few minutes of conclusion. So first of all, general game playing is not a game. I've kind of argued that. It's not just about playing games. There's a more fundamental reason for studying all this stuff. It has to do with how we build programs that can write programs. And that's useful in a variety of real-world settings where game-like rules are the specifications that our systems are given. And that happens in a few cases. One case, for example, in businesses. When you're running businesses, they have so-called business rules, pricing rules, rules for whether you can be reimbursed for an expense without getting your manager's approval. You can do that, let's say, if it's less than $1,000, or whether you're allowed to buy a thing without getting a manager's approval. There's all these rules that businesses have about how they do their work. Or you have rules for how you do business with your customers. You have to keep that guy's stock full every month, or you have to make monthly deliveries, or you got to keep it full. There are various different contracts you form with other enterprises. And those take the form of rules that are very similar to the rules of general game playing. And one can codify those, and what we like to do is to have our enterprise management systems take those rules and build systems that will actually run the enterprise, rather than having to hire Java programmers to do that. Another example of that outside of the context of the enterprise is computational law. Maybe we can do the same thing with the laws of society, governmental rules that tell us what we're allowed to do. Can we buy that drug from Canada? Can we ship this alcohol to Virginia? All those rules should be built into the system so that as they change, you don't have to hire another team of programmers to go and rewire the Java code. The system will just adapt to the new rules. So this is really what it's all about. And there are governmental agencies as well as companies that are interested in this technology for that reason, not because of the inherent interest of game playing or the educational values of game playing. All right, and so I'm going to close up with just one slide if you were in CS, you would recognize these people. If you're in AI, you would recognize these people. I'll just tell you who they are, and then I want to point out what they had to say. So early in 1950s, these two guys, Alan Newell and Herb Simon, one of the first the people working in AI were building game playing programs, wanted to build something called a general problem solver, which would demonstrate how generality can be achieved by factoring the specific description from the of tasks from the task-independent processes. So what they had in mind was there was a program you could build, and you would give it a description of what you wanted to do, and it would just do that. The description wouldn't be a program that tells you how to do it. It would just do it. It would just be what you want to do. So the idea was to separate what's called what versus how. What do I want you to? What do I want to have happen? You figure out how to do it for me. That was their notion of general problem solving. Well, just replace description of task with description of game and call that general game playing, and you have exactly what these guys are talking about. And they were influenced to a large extent by, maybe if you wanted to take a father of artificial intelligence, to be John McCarthy, who back in 1958 wrote this paper called The Advice Taker, where he laid out for us all the ultimate goal of artificial intelligence as he saw it, which was that he wanted to build a program he called it an advice taker, to have advice taker, the advantage we have is that its behavior can be improved merely by making statements to it. You tell it about the world, you tell it what you want, it does it for you. You don't have to program it, you don't have to have Java programmers, you just tell the machine, it does it for you. General game playing is an attempt to achieve that goal in a setting which engages our interest in games and is bringing people into the field because of the fun of playing games, but actually is working on McCarthy's long-term vision for the field. That's it.